All right. I still feel like I'm trying to play catch up in this class, trying to get us, back on track since we had that whole week of not really being focused on the material. So in the other pre-cal class, one of my colleagues just gave their second exam yesterday. So I'm like, we're not even really close to that yet. I think we have another, let's see, according to my schedule here, we got to cover this, and then there's another 2 sections, and then we have our exam. So we've got another good 3 days of lecture before we can get our next exam in, and we will have a review day before that exam. So, it says on our calendar October 27th for our exam, and I really don't think we're going to meet that. I think it's going to be after Halloween. So, but we'll see. Let's just see how things go, okay? So today we did our quiz. Can y'all see the board okay? Do I need to kill another light? You want to kill another light? Yeah? There we go. So today we did the unit circle. Now we're going to focus on graphing two of the trig functions today. Remember, there's 6 trig functions: sine, cosine, tangent, cotangent, secant, cosecant, right? All 6 of those. But the key to graphing all 6 is to at least get the first 2 down. Once you know sine and cosine, everything else kind of follows from those 2. So we are going to continue. Last class, we had begun talking about it at the very end of class. I don't know if you remember this, but I had talked about back in my college algebra, we define a function, f of x equals something, and then from that we created the t-table, right? We had the input, that's the x, and then the output is what the function spits out. And then we graph these as points, and we graph them on an xy axis, right? Talked about that. And then we said, well, if we define a function f of theta to be sine theta, then we could do the same thing and make a t-table, and then we could go graph those, right? Graph those as points. Yes, yes? Okay. And then what I did is I brought this up, and this was how we could relate the actual unit circle to the graph. So these are completely 2 complete different pictures, but they are giving you kind of the same information. For this unit circle, sine of the angle is always which coordinate? Sine of the angle is always the y coordinate, right? So it's the height of that point. So as I start to rotate this angle, or rotate that point around the unit circle, the angle is the thing that's changing. So the angle is the input, right? Angle is what goes into the function. What comes out is the height, that red distance, right? That height is our output. So if you look at that green thing as being the in, and the red thing as being the out, then if we just transfer those pieces of information down to an xy axis, then what we have is the green is the x value, that's our angle, and then our y value is just this height. So 0.5 matches this height right here. Do y'all see the connection? Okay, so as I go around, I did this last time, as I go around I can kind of keep those points there so you can kind of see what the picture is going to look like. Then once I get to a full revolution around, then everything's going to start repeating itself, right? Now my angle is going to keep getting bigger, isn't it? My angle is going to keep getting bigger, so I'm going to keep going out the x-axis, but my graph is just going to do a repeat of what it just did, and then a repeat again, then a repeat again. So technically this sine function goes out to the right forever and just continues that pattern. So we call that a sine wave. If we connect all the points in between, then we get that picture. So notice that my sine curve continues like that, and then I have to at some point stop. So I stop there. And then also, remember that you could always rotate your angle backwards. Like, we didn't have to go counterclockwise. We could have gone clockwise, which would have been a negative angle. So if I go negative angle here, right, now notice my input's negative. So on the x-axis, I'm negative, but my y value here, I still have a distance here, a y value, so that's this distance right here. So that sine curve goes in this direction forever also. Make sense? No questions? Okay, so let's talk a little bit more about this sine curve. Then we'll take a look at the cosine, see how the cosine is different. And then we're going to start to try and graph functions that are not as simple as just sine. Like it'll be, maybe we'll change it somehow so it's, you know, makes it a little taller, makes the waves a little tighter, whatever it may be, all right? So this note for today, because that's where I ended last class right there, the note for today is going to start at 7, 6. I'm going to start a new page. 763. Okay. If y equals f of x equals sine x. So please notice that I've changed something here. Instead of using theta, I'm using what? Instead of using theta, x, right? So I'm not saying that our function is f of theta anymore. I'm saying it's f of x. X is still the input here, right? X is still the input. The input is still going to be an angle because we're plugging it into sine, so we have to look at that as being an angle inside. What are some of the properties of this? Well, we should all know that the sine function is going to start out at 0. It's going to go up, come back down, and go like that. That's what every sine function is going to look like. Or that's what sine of x is going to look like. Now, it goes in both directions, so I'm just going to put little dotted like this just to kind of let you know that it does continue, okay? And now I'm going to start listing out some of the properties of this function. And I'll list them to the side so I can try and get them all on one piece of paper. First of all, the domain. The domain of a function are all the things that you can plug in, right? Or if you look at it in terms of a graph, you ask yourself, where does the graph exist? So look at your x values, and you start moving to the right. Do you have graph over here? Yes? How far does it go? Forever. How about to the left? Same thing, right? So since your graph goes to the right forever and to the left forever, and there's no breaks in the graph, the domain is everything. So we say that either one of two ways. We say it's either negative infinity to infinity, or we could say that double struck capital R to mean all real numbers. Now that means, what that means to you, and this is important because of where we're going to go in a little while, is that you can plug any number into a sine function and it will spit out an answer. Because what you're plugging into the function is an angle. And so you can plug in 0, you can plug in any positive angle, and you can plug in any negative angle. There's nothing you can plug in that the sine function cannot handle. That will be different when we get to something like cosecant. Because cosecant is 1 over sine, and then you could get division by 0, and then weird things can happen. So we, just again, because of where we're going, let's kind of keep in mind that that is important to understand domain now. All right, the next thing is range. The range is the output of this sine curve. That's your y values. So what's the highest value you can ever get? What's the largest value you can ever get out of sine of x? 1. What's the smallest? -1. And do you get every value in between those? Like, will your sine function ever be 0.7? Will it? Let me label this up here. This is 1, right? Down here is -1. Will it ever be 0.7? Yeah, somewhere, right? I can't tell you exactly where it would. You don't need to put this down here, but it will be 0.7 somewhere, right? It will be 0.756799952, right? Somewhere. I don't know where, but it will achieve that value. So the sine function, the range of it, the outputs, is everything between -1 and 1. And why do I use a bracket? Because it includes 1 and -1. It will achieve 1. It will achieve -1. Why did I put parentheses on the infinities and not brackets? Because infinity is not a number. All right? See, 1 is a number. You can get to 1, can't you? You can get to 1. You can stop at 1. You can't ever get to infinity, so you can't put a bracket because you can't stop at it. It just keeps going. So the idea is that it goes forever, so you don't put a bracket. Right, so those are the first two things. Now, the third thing is what we call the period. Now, when we say something is periodic, you know, like your monthly bills, or, you know, what are things? The sun coming up every day, right? Periodic, it happens at certain intervals, right? It repeats itself. Well, we want to know, when does this thing repeat itself? What distance does it take for it to start repeating? So if we measure from where it started to where we got to the end and where it would start repeating itself. So right at this point, it would start drawing the exact same thing, right? And then after another distance, it would do the same thing. So we want to know, what's that distance? So what is the distance in which it achieves its full picture? And then everything else is just a repeat. So what is that distance? 2 pi, right? That was drawn when we did our graph here. When I started at 0, come back. Okay, that's where we started, right here. It's going to go up, come down, come back, and then it'll start repeating. So that took a full revolution for it to actually do that. There's my full revolution. After that, it's going to repeat. So that took 2 pi. So between 0 and 2 pi is the distance. So that is our period. So this is 2 pi. What's another way of saying 2 pi? In degrees, that would be 360. Now, nobody has asked me this, but if the x-axis is the input's an angle, right? The input is an angle. Then is our x-axis in degrees or in radians? That's going to depend on you and how you want to graph it. If you want your x-axis to be in degrees, you need to label everything in degrees. This point here would be how many degrees right here? 0, what would that be? Well, 180, right? That's halfway across, and this one would be 360. But you would have to put degree symbols. Now, I can tell you right now, most of the time, we do not ever use our x-axis in degrees. We usually use radians. All right, so I've seen it done before with degrees, but not very often. So be prepared to see a lot of radians in here now instead of degrees. Okay, so that's our period. Every 2 pi, it repeats itself. The next thing, X-intercepts. The X-intercepts, I'm going to put X-int. The X-intercepts of a sine curve is everywhere it hits the x-axis, right? Hits or touches. So I see X-intercepts here at the origin, right here, right here. But remember, the curve keeps going, right? Doesn't it? To the right forever, and it keeps going to the left forever. So where does it hit the x-axis? Can you tell me, like, in general? Let's make a list of where it hits. X equals 0, right? Where else? What's halfway here? That's pi, so 180, right? I'm going to put pi here, and then here was 2 pi, so I'm going to list them out here. Pi, 2 pi. Where would the next one hit? Out here somewhere. Where would it be? 3 pi. Then the next one, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, right? I'm going to say ... that it follows that pattern. Do y'all agree with that? What about the other direction, though? Where would it hit? Negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So here's the way that we would write this, okay? We could list out all the negative ones also. So I could say like negative pi, negative 2 pi, negative 3 pi, and then I could say ... like continue that pattern. But this becomes too tedious to have to list out everything. So here's the preferred way to write the answer. Instead of that, you just say x is, how can I tell you every multiple of pi? Because isn't that every multiple of pi? That's 1 times pi, 2 times pi, 3 times pi, 4 times pi. All of those, and the negatives. So what we write is this, k pi. where k is an integer. What are the integers? What are integers? Whole numbers. Is 0 an integer? Yes. Is -1 an integer? Yes. These are the integers, just so you know. 0, 1, 2, 3 forever, but also -1, -2, -3. So if I say that all of the x-intercepts look like k times pi, where k is an integer, then you're letting k be all of these. So first let k be 0. If k is 0, what do you get? 0. If k is 1, you get pi, 1 pi, and then k is 2, you get 2 pi, and then you get 3 pi. So do you see how this is a very condensed way of writing all of those answers, all of them, every single one of them? Yes? We'll be doing that a lot in this class. All right, now, writing this out, x equals k pi, where k is an integer. Another way you can write that, that's more condensed than that, is say k pi, where k, okay, it's like a backwards little e here. K is an element of double struct capital Z. Now, what was double struct capital R? Double struct capital R was all real numbers, right? Double struct capital Z is all integers. So this is a way of representing all integers. It's a shortened way. Now, if on a test you write all the x-intercepts are x equals k pi, I understand what k is. You don't need to explain it to me, all right? But I want you to understand what k is. K cannot be 1/2, right? K has to be an integer. So to just write k pi isn't really enough if somebody else is reading what you're trying to write. But we will understand in this class from here on out that if we write k pi or anything like that, if we use k, we all agree it's an integer. That fair? Okay. All right, so that's where we get all the x-intercepts. Questions? The next thing we're going to look at is let's see, this is 5. Try and squeeze 5 in right here. Okay, now this sine curve, we said that it goes up, then it comes down and up and down. The highest point that it ever reaches is 1, right? And then it comes back down, then it goes up to 1 again, then it comes back down, goes up to 1 again, comes down. So that keeps happening, right? That keeps happening? My question is, where does it hit 1? So where is it 1? At pi over 2, right? Pi over 2. I'm going to label that on my graph, pi over 2. Where else does it hit 1? Over here, right? Do y'all see that? It's over here somewhere. And then isn't there another one further down the road? And another one further down the road? Yes? Do you agree that it's somewhat challenging to figure out where all those are? I mean, like the x-intercepts, I think was pretty clear. 0, pi, 2 pi, 3 pi, 4 pi, right? But those are a little bit more challenging? Yay or nay? A little bit? So what I recommend is instead of looking at this, go back to where this thing came from, okay? Where does it come from? It comes from this idea, right? When you're saying, I'm trying to figure out where sine is 1, right? I want to know what angle gives me sine 1. Where are you? Where is the y-coordinate 1 on this? At what angle? At pi over 2. Get back there, damn it. Okay. Everyone agree? Now, we know that it'll be 1 again if we come and swing all the way back to it, right? Or if we come and swing all the way back to it again. Or we could have gone backwards and come to it, right? So instead of trying to read the graph, let's read this. And let's go back to the note and let's say, see if you can follow this logic. I know that it'll hit its max value at pi over 2, right? Definitely for sure, we all agree with that? But I could swing all the way back around and get back to that point. So I could add how much to this? 2 pi. But I could have added another 2 pi and come back around again, right? So I could actually, this 2 pi represents a full rotation. So I could start out pi over 2. I could add 1 full rotation, or 2 full rotations, or 3 full rotations. So what should I tack on to the end of this to make it give you all the answers? K. Because I'll put it in a different color, times K. Do y'all see the importance of K here? Pi over 2 is straight up and down, right? If K is 0, what's your answer? Because remember, the K is an integer. If K is 0, what's your answer? Pi over 2. And we already said at pi over 2, you're at 1, right? Now, if I let K be 1, then I'm going to take pi over 2, and I'm going to add 1 full rotation, right? Well, this way. And I'll still be back there, won't I? If I let K be 2, I'm going to add 2 full rotations to pi over 2. So I start at pi over 2, I do a full rotation, then I do a second full rotation, I should still be back there. That's only one answer. You mean, why do I need all this? Because if we're asking where the sine function is 1, the sine function this is the sine function, all right? Now, what I've done is I've drawn several periods of the sine function. So you have, here's your first period, so that's 0 to 2 pi right there. Then here's the second period, then a third period, and then the periods are going backwards too, right? So if I ask you where does it hit 1, where's your sine function 1, it's here, 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 and they go in both directions forever, don't they? So I need your answer to be an infinite list of answers. You could just give me one answer, but that's only one out of infinitely many places. Does that answer your question? But I think the most useful way to get to it is to say, you're saying to yourself for this problem, you're saying, at what angle, right, is sine 1? That's what you're saying to yourself. If I want to know when the max value happens, I want to know at what angles the sine is 1. You go to the circle, and sine being 1 meant y coordinate is 1. You say that's pi over 2, and then from that, you know to get back to that angle, you just add full rotations. Does that make sense? I'm hoping I'm clearing that up. And when we say full rotations, we could go around this way, or we could have gone counterclockwise, which would have meant we subtracted 2 pi, which is why the integers would work, because this allows us to subtract 2 pi, or subtract 2 pi's, or subtract 3 2 pi's, so on and so forth. All right, I need to keep moving with this, so I want to make sure everyone's on the same page here. Yes? Now, I'm going to actually simplify this answer a little bit. I'm going to clean it up. Watch what I do. I want to put these together, because right now they are 2 terms. Try and put it into 1. So I'm going to rewrite this as 4 pi k over 2. What did I do there? What did I do from here to here? I looked at that 2 pi k as 2 pi k over 1, right? And then I multiplied the top and bottom by 2. Why? Because I'm going to put them together. So I was trying to get a common denominator between these two so I can smash them together. You'll see the value of this in just a second. But are there any questions on what I did? Okay, now, if I say, put those together, don't I combine the numerators? I add the numerators, so pi plus 4 pi k over the common denominator, which is 2. You cannot put pi plus 4 pi k together, right? They are not like terms, right? These are not like terms. You can't make this 5 pi k. This is pi plus 4 pi k, and you leave it. Now, why in the hell would I want to do that? Well, here's why. What if I ask you to give me 6 different places where it's 1? 6 different places where the sine function is 1. Then if you just go with this answer right here, first you plug in 0 for k, and what would you have? If you plug in 0 for k into that one, you just get pi over 2. Now you plug in 1 for k, and what do you have? Pi over 2 plus 2 pi, and then you have to actually put those together, don't you? Get a common denominator and put them together. Pi over 2 plus 2 pi. Right? You can't add those until you get a common denominator. So you do that, and you'd figure out the answer. Then you have to give me another answer, so you let k be 2. That would make this, what, pi over 2 plus 4 pi? And then you'd have to get a common denominator again and add them together, wouldn't you? And you have to do that for all 6 answers, which is a pain in the ass. So instead of doing that, why don't you just get a common denominator right away off of this general answer, and then now watch how easy it is. Plug k in, k is 0 in here. If k is 0, what do you have? Well, this is gone, right? And you just get pi over 2. Let k be 1, what do you get? You get pi plus 4 pi, right? Which is 5 pi over 2. And you're done. You don't have to do any more work. If k is 2, what do you get? So this is now going to be 8 pi, right? So 9 pi over 2. And you could keep going, couldn't you? You see how much faster these answers come out? Okay. We could also let k be negative numbers and do the same thing. Let's do one negative one. If k was negative 1, then you would have what? Pi, then take away 4 pi, so negative 3 pi over 2. Pardon me? Okay, so I'm replacing this k right here with these different values. So if k is 0 right here, doesn't it kill this off right here and make it a 0? And what's pi plus 0? Just pi. What's pi over 2? Just pi over 2. If I let k be 1, then this is just 4 times pi times 1, which is 4 pi, plus a pi, that's 5 pi, then divide by 2. So now I have 5 pi over 2. Do you see it? Oh, yes, yes, I'm sorry, yes. You can't combine them here. Once you let k be a number, then they can go together, yes. Now, if I go back to this picture that I had, where is it? There it is. Take a look at this. It's hard to see it here, but at pi over 2 was one answer, right, that we got? And we just got for the negative one, the other direction, right? What did we get? Negative 3 pi over 2? And that's here, and you can see that's right there. It worked. And you just have to trust that if you kept on going, you could get them all. And since you can't write an infinite number of answers, the general solution with the k in it is the preferred answer, because it gives you all of them. Make sense? Okay, so that's where we have a max value of 1. Right here. This is where the max values occur. Well, it has a max value, but it also has a minimum value. What's the minimum value? I'm going to have to go to a new page. The min value of negative 1 occurs at, yes. No, I'm keeping the max and min. I'm keeping them together in the 5th one. So I'll have a different one for the 6th. Okay, so what I recommend, again, you look at is go back and say, look, this is the sine function we're talking about, right? Where does the sine function take on the value of negative 1? So go to your circle, right? That's at 3 pi over 2. Here it is. So you look at the circle. How do I know it's 3 pi over 2 down here? Because sine is the y coordinate, right? So I want to know when is the y coordinate -1. Well, it happens right there, right? There's where my y value is -1. That happens at 3 pi over 2. That's one answer. How do I get all of them? How do I get every answer, 3 pi over 2, and all of the rotations that would take me back there? 3 pi over 2, and then add to it 2 pi k, right? 2 pi k. Y'all need to let me know if this is making sense or not, because this is like, if not, it's like trying to run the rest of the race without a leg here. It'd be, oh, after you put it together. Yes. In this particular case, it would. Anyone else? I mean, this is what gets us, that's what gets -1 to come out one time, right? I need to be able to swing all the way back around possibly and use that angle also. So I need to keep on adding rotations, and I can go either way, but full rotations, yes. We would add 2 pi to this angle, and we would still be at the same place, right? It would be a coterminal angle than the k, because k takes every rotation, positive and negative. So I want to kind of start talking in the language that I'm going to be talking later. Sine is -1, right? Sine is -1 at 3 pi over 2, plus any full rotation, right? 3 pi over 2 plus any full rotation. When I say that, I mean our answer is going to be 3 pi over 2 plus any full rotation is 2 pi k. So I'm going to put here, this will happen when x is equal to 3 pi over 2 plus any full rotation 2 pi k. This is a full, all or any full rotation. Now you put them together with a common denominator. And so you get 3 pi plus 4 pi k over 2. That's what you were saying, right, sir? Okay. And that's it. That you cannot combine until you plug in a value of k. Once you plug in a value of k, then you can start putting them together and you get your answers. This is such an important idea, all right? So important, I want to ask you a separate question. So I'll come back to this note. I want to just get to see if you understand this or not, all right? When is sine of x equal to 1? Not 1, sorry. When is it equal to 0? So this is the way that I would approach it, all right? I go back to my unit circle. Terrible circle. And I'd say, when is which coordinate, the x or the y am I looking at here? Y, because it's sine, right? So I say, when is the y coordinate 0? When is the y coordinate 0? Do you all agree it's actually at 2 places? Yes? The first place at 0 is at what angle? The one to the right? What's that angle to the right? 0. What's the other angle? Pi or 180, right? Let's stick with radians, though. 0 or 180. So what I could do is I could say, go to 0, do full rotation, 0 full rotation, 0 full rotation, right? But then I'd also have to say, go to pi, full rotation, pi, full rotation. There's a more efficient way, though. Do you see it? Aren't those angles directly across from each other? Like those points are directly across? So couldn't I start pointed out this direction And then to get to the other one, how much would I have to add? Just a half rotation, right? Just pi. And then how do I get back there? Add another half rotation, right? Then how do I get back there? A half rotation. Then how do I get back there? Half rotation. Do y'all see that? I could have gone the other way, this half rotation the other direction. And it keeps, so if I start out pointing this way and keep adding half rotations in either direction, I get all the answers, don't I? So that's the way I'm going to approach this one. I'm going to say x here will have to be, well, what's pointed out to the right? 0 plus, how do I say a half, all half rotations? Pi k instead of 2 pi k. Right? 2 pi is a full rotation. Pi k is a half rotation. So I don't need the 0 there. Pi k. Now let's start looking at some of the possible answers here. If k is 0, what do you get? If k is 1, what do you get? Pi, k is 2, 2 pi, 3 pi, 4 pi, right? And then you can do all the negative ones. Well, wait a minute. Isn't sine x equals 0? Aren't those just the x-intercepts? Look, when I'm saying when is sine 0, it's this x-intercept, this x-intercept, this x-intercept, isn't it? Whenever you set a function to 0, you're saying where it's x-intercepts. We answered that question earlier, didn't we? In our first beginning of this, I said, what are x-intercepts? And we did it by looking at the graph, didn't we? And we got all these. I said, oh, the answer is going to be pi, k times pi. Yeah? Do you see that? Well, you tell me. Do you think looking at the unit circle instead was easier or not? I mean, that's a question you have to ask yourself. I think everything can be generated off the unit circle. That when someone asks you, when is sine equal to this, you don't need to go to its graph. You just go to the unit circle and you can figure it all out. All right, a couple of other things about sine. Let's see, now we're on the 6th thing. The amplitude. Is 1. And the way we look at amplitude for sine it comes off of, it goes between 1 and -1, like this. It's this distance right here. Ooh, that's supposed to be a brace. It's that distance right there. From the x-axis up to the highest point. And it's a distance, right? And since it's a distance, it'll always be measured as a positive number. So your amplitude is always positive. Now later on, we're going to change the amplitude of the sine function so that it's taller or shorter. But just remember that the amplitude is always positive, and it's always that distance right there. It's not the distance from the top all the way to the bottom. That would be twice the amplitude. All right, last thing on this. 5 important points. There are 5 points on every sine curve that are absolutely critical. In fact, if you know what these 5 points are, you can draw the rest of the graph. So what I would like to do is point them out. And I'll point them out on, I'll draw a new one real quick. Here's my sine, like this. It's 2 pi out here. We said halfway was pi, right? Here are the 5 points. I'm going to exaggerate them here. We have these 3 x-intercepts, right? We have 3 x-intercepts. We're talking about one period here, right? One period of this sine curve. In one period, you should have 3 x-intercepts. You should also have a maximum point. So one maximum. And you should also have one minimum. Our ultimate goal here today is to be able to graph these by hand. And so to graph them, what we will actually do is we will find just those 5 points. And once we have those 5 points, we can kind of tell what the rest of it looks like, and we just connect them with a nice curve like this. We just have to be careful later that when we do this, that we draw it like a curve. We don't draw it like lines where you have like, you know what I'm saying? Like if I got 1, 2, 3, 4, if I got those 5 important points, we don't come in here and go like this. Like, it's not that, right? It's a sine curve. All right, go with me? All right, now 764. Y equals f of x equals cosine x. So what's the difference between sine and cosine? Well, on our circle, sine was the y coordinate, right? Cosine was the x. So when we go and start to draw this, or try and draw it, let me bring up my cosine one. So the input is still the angle, but the output now is the x-coordinate. So you can see here at 0, we're at this point, the x-coordinate there is 1. So look at my graph. At 0, I'm up here at 1. And as I move around, what happens to my x-coordinate? It's going to get smaller and smaller, right? Until I get straight up and down. When I'm straight up and down, what's my x-coordinate? 0. So watch my dots go around here and see how it matches up there. So x is getting smaller. And what I'll do, see if this helps. Okay, so the x-coordinate is getting smaller, smaller. It's 0. Then it's negative x values because I'm in the second quadrant. Negative, they're getting bigger and bigger and bigger. I get all the way over to what? -1. So I'm down there on the graph. Then I start coming back. I'm still negative x values, but they're getting smaller, so they're coming up over here. And then I get to 0 again. And then now I'm in the fourth quadrant, so my x values are positive, and I go all the way back out to 1. And if we bring in the graph, that's the graph of cosine. It looks very much like sine, doesn't it? But sine started at 0, went up and then back down and came back at 2 pi. This one starts where? At 1, and then does the same sort of thing and ends at 2 pi and then starts to repeat itself. But the graph is very different though, right? It's not exactly sine. It's related, but it's not the same. So, what are the properties of this cosine function? We'll draw it first. You're always going to have pi, 2 pi. It'll always be between 1 and -1. It will start out up here at 1. It will end at 1. Okay, that will always happen. It'll start at 1, end at 1. And then at halfway point at pi, it's down at -1. At the quarter point, so what I mean is at pi over 2 and at 3 pi over 2, it's at 0. On your drawing of these, try and get somewhat decent at these. Look, between here and here, okay, your graph should look like the right side of a frown. You know what I mean? Like happy face, sad face. Here's a happy face. Here's a sad face. Right here, this should look like the right side of a frown, right? That right side of the frown. And then right when you get to that point, it needs to start looking like the left side of a smile. And then the right side of a smile, and then the left side of a frown. And you may be saying, "Ooh, okay, that's kind of cheesy to be thinking of it that way, smiles and frowns." But in calculus, that's called concavity. And this would be considered to be concave down, concave up, concave down. And you actually graph things by hand using that property of that sort of curve. So I'm not just kind of making it up because it looks like a smile or a frown. It's mathematically later you do that. So I just want you to kind of get used to drawing it properly now. All right, let's talk about those 6 things. And we'll go faster through this. What's domain? Everything, right? All real numbers. What's the range? -1 to 1, same thing as before, right? Same as sine. What's the period? It still is the same period, right? Every 2 pi, it repeats itself. Everything's exactly the same as sine, right? Up to this point. Okay, here's where things get not interesting, but where they change. What about x-intercepts? Okay, forget the picture. Don't look at this. X-intercepts. I'm really asking you for x-intercepts. When is cosine x equal to what? When I'm saying x-intercepts. When is it 0, right? That's what I want to know. So I'm trying to teach you that instead of looking at this, that you should go look where? The unit circle. Go to your unit circle. Draw a little mini unit circle like this. And then say, when is cosine 0? So which coordinate am I looking at? On the unit circle, which coordinate is cosine? The x-coordinate. I want to know when the x-coordinate on this circle is 0. Where does that happen? Straight up and straight down. Do you all agree that at those 2 points is where cosine is 0? Okay, how do I get to those points? To get to the one straight up, what angle is that? Pi over 2, right? Pi over 2. How do I get to the one below it? That's 3 pi over 2, right? So I could, again, start here, and I could go all the way around to be back there, all the way around, but what's more efficient in this case? What could I do? I could just add a half rotation to get down here, then another half rotation to be back up here, half rotation. So how about start out at pi over 2 and add to it what? Pi k. If I let x be equal to pi over 2, and I add pi k to it, I should get all possible answers. Please, any questions? So what if I asked you for like 5 answers? Give me 5 answers, 5 places where cosine is equal to 0. You can just start plugging in values of k, right? 0, 1, 2, 3, 4, whatever. Would this have been okay? I'm just curious if you're really understanding this. Could I have written this? Would that have been an acceptable answer? 3 pi over 2 plus pi k. Yes, because what's happening is instead of saying I'm going to start here and keep adding half rotations back and forth, I'm actually going to start here and add half rotations back and forth. I'm going to get all the answers still, though, because k can be any integer. I'm eventually going to wind up with this answer, pi over 2. Question? Pi and not 2 pi? How much of a rotation does it take to get from here to here? A half rotation is pi. If it's the full, it would have been 2 pi. So I guess the moral of the story here is this so far. If your answers, the places that are going to solve your equation, if they're directly across from each other, you always just find one and add pi k to it. If your answers is just one answer and you have to come all the way back around, you're going to add 2 pi k every time. And there are going to be situations, we're not there yet, there's going to be situations where we have something like this, where your answers are here, 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 and here. And these are across from each other, and these are across from each other. How would you get all those? See if anyone's really getting this or not. Start here. I could actually go pi over 2 to get to this one. Then another pi over 2 to get to this one. Then another pi over 2. Do y'all see that? Another pi over 2. So if I do whatever this angle is, what is this angle? The way it looks at least. Let's pi over 4, and I add to it pi over 2 k, I get all those answers. We'll have more time for this, don't worry. All right. So that's the answer right here. This is where I have x-intercepts. Where do I have maximums? So this is 5. Where do I get max values? The max value of 1 happens at what? So you're going to go draw a unit circle, right? I'm trying to figure out when cosine is 1. I want to know when cosine is 1. When is cosine 1? What angle? So you're looking at which coordinate here on the unit circle? Cosine's always the x. When is the x value 1? What can be a little weird is that this x might throw you off. Forget that it's an x. Just when is cosine 1? When on your unit circle is your x value 1? 0 degrees, right? Anywhere else? 2 pi. So, but nowhere else other than that one, right? Every coterminal angle would work, but nowhere else on that unit circle is the x-coordinate 1. So how am I going to represent that answer and all infinitely many of them? 2 pi k. I'm going to add 2 pi k. To what, though? What am I adding 2 pi k to? What was that angle to start with? 0. So I don't really need it, right? So your answer would just be 2 pi k. But this is just to point out. That's right. And that would still give you the 0. So this is just to show you 0 is where I started, right? Pointing out the right side, that's 0. And then I'm adding full rotations to get back to it, 2 pi k. So your answer is 2 pi k. How about its minimum value? So that means I'm trying to figure out when my x-coordinate is what? -1. So I go to my unit circle. Where's my x-coordinate -1? It happens at this point, right? So just by a show of hands, how many of you right now could, if I said, like, take out a sheet of paper, quiz, tell me the answer to that, how many of you feel like you could really do that right now? Tell me the general answer is this. That's it? 2 people? Could tell me the answer is this? 2? Really? Yes or no? Just 2 people? 3? 4? 5? So what is it then? How do I get to this point? What's the angle that gets me here? Pi. And how do I get back there? Plus 2 pi k. Yes, that's it. So I just have to start at pi, then I have to add a 2 pi k to that. So pi points me to the right. To the left. That's my pi, and then I just add full rotations to get back to that, either direction. I can't put those together, right? Not right now. I'd have to wait till you plug in a k, and then you could do it. All right, what's the amplitude of the cosine function? Amplitude's still 1, right? I'm just going to put amp 1. And then for 7, it has 5 important points. What are the 5 important points for the cosine? How many x-intercepts do I have for the cosine? I have 2 x-intercepts, right? Maximum, 2 maxes, and then 1 minimum. That's it. Okay, we have about 20 minutes. I'm going to see how much of graphing these I can get done. So we are in 7.65. All right, so I've noticed a few of you falling asleep in this class, and I'm not a big fan of sleeping in this class. So if you're really tired to the point where you can't stay awake, I recommend you just go outside, do a couple of push-ups, do a couple of jumping jacks, get your blood flowing, come back into class. From this point on, I'll have no mercy on sleeping. All right? Penalty. There will be a penalty. What was the penalty that Ms. Schmidt had for it? Did she have penalty for sleeping? No? Then I'll just embarrass you. All right? In my classes, it's a 10-point penalty on your next exam for sleeping and for texting on your phone. So wake up, ask questions. The reason I asked how many of you could get 100 on a quiz is because for the people who were sleeping, I felt like if I gave a quiz on that spot, they would have no idea what I was doing, and they would get a 0, and everyone else would get hundreds. So I was trying to teach a lesson there, and I will do that if I have to, if people aren't paying attention and not answering questions, okay? I don't want to put you on the spot, but I'm asking for interaction here. I need to know if you're with me or not. All right, let's try and graph. If we change things, let's say we have something where instead of just y equals sine x, we actually put a number out in front, like a in front of the sine, and we put some number inside there like b. Y'all see the differences? The a and the b there? Okay. Well, here I want everyone to realize that the a and the b are just going to be numbers, all right? So they're not new variables. This is like a general picture of what could happen. I put a number in front of sine, I put a number in front of the x. How does that change the graph? Well, the a controls the amplitude. In fact, if the absolute value of a is bigger than 1, then it stretches it vertically. It makes the sine curve taller, okay? Makes it taller. If the absolute value of a is less than 1, so like a fraction, 1/2 or something like that, then it's going to shrink it vertically. That's what a does. The b controls the period. specifically, if we have b here, a number in front of x, then what we will do is we will compute, or we will calculate the following value. And we'll call it p for the period. P will be equal to 2 pi over b. So what is the period of the normal sine curve? What's its period? 2 pi, right? Well, in the normal sine curve, what's the b? What's the number in front of x in the normal sine x curve? The number in front, it's 1, right? Like if I just write y equals sine x, right? What's the number in front here? 1. So that makes sense that the amplitude would be 1. And then what's the number in front of x? 1. If I take 2 pi and divide it by 1, what do I get? 2 pi, and the period's 2 pi. Now, if we change those, it's going to change the picture. Okay? So here is, where's the one I had for that one? Close that out. Close that out. What a mess. There we go. Okay. So take a look at this. This is our normal sine curve. Y equals, now I'm exaggerating. What's the a in front here? It's 1, right? What's b here? 1. So this is just our normal sine curve. Y equals sine x. We've got our period 0 to 2 pi, right? It repeats itself. I'm looking backwards also. So watch what happens if I change the amplitude. If I take this, I'm going to grab this and slide it. If I make that amplitude change, so what's my amplitude right there? 1.7, right? So now it's taller, right? Here's 1. Now it's a taller curve. What's the period? Still 0 to 2 pi, right? So it's still 2 pi. So that period's not going to change if I adjust the amplitude. If I make it taller and taller, well, can't really see it, so I can zoom out a little bit. Make it taller and taller and taller, right? So that's what the amplitude does. That's what that a adjusting the number in front does. Now, we go back here, bring this. Let me now adjust the b. So what if I make that right there, that number, a 2? What should my period be? Just pi, right? Because I'm supposed to take 2 pi and divide it by b. What's 2 pi divided by 2? Would just be pi. So let me change that. I don't remember how I did this. Oh yeah, 2, there. So look at my period now. Here's 0, here's pi, here's 2 pi. Look what it does. It goes up, comes down, comes back up. There's your period. It's done an entire sine oscillation, right, in a shorter period of time. And then it does another one. So you actually, in 2 pi, you actually have 2 sine curves smashed in there, right? If I change it to 3, my period should be what? 2 pi over 3, right? Which is just 2 pi over 3. So this one's going to be harder to see. But if I go up, I come back down, I come back up, where it hits right there, you know, see my little arrow there? Right there, that should be 2 pi over 3. What if it's 4? What's the period going to be? Pi over, so it's 2 pi over 4, so that's pi over 2. So this should be in pi over 2. There's pi over 2. Let's see, I start at 0, I go up, come down, come back up, boom, there, pi over 2. So I actually have what? Another one here, then another one, then another one. So I actually have 4 sine curves smashed into a smaller space. What is this called? These people who understand like waves and radio signals stuff, what is this called when you change this part of a sine curve like that? Frequency. It's your frequency. It's how often, how smashed together your waves are. Right? Yeah? When you're changing your radio station, right? And you're going from 90, what? I don't listen to the radio, so 90 what? 99.5 to 98.5. Okay, so if you're doing that, right, that's FM, right? FM. FM stands for, what's FM stand? Frequency modulation. You're changing the frequency from a frequency of whatever you said, 89.5 to 99.5, whatever you said, right? You're changing it so that your receiver is looking for waves within that certain frequency, and then it converts that over to the sound. Now AM amplitude modulation instead, so it's looking more at the amplitude. So it's there, it's hidden in our lives, it's not very relevant. We just turn it on and say that song sucks and go to a different one or whatever, but this whole idea of how tightly packed together these waves are and stuff is how we communicate. You know, it's how we listen to the radio. So it's very useful being able to adjust this. Got it? So there's so many stations. There's only so many stations because there's only so many frequencies within a certain range, right? And so you don't have like FM channel 374.2, right? They keep it all within a certain range. There's only a certain radio frequency range that you can be in. All right. Going off on tangent here a little bit. So let's try and see if we can get a quick one graph done in the next 10 minutes. I know it's a lot of me talking today and not a whole lot of practice, but here we go. This is our first example. Y equals 4 sine 2x. I want us to sketch this. I should have said this, but let's sketch it. And I want us to include in this sketch, I want us to include 3 periods. So it's going to be 1 period, and then we're going to extend the period in each direction. You'll see. I'm in next class when I have more time, I will give you the actual set of steps on what we will do to graph these things. But right now I'm just going to run through them. The first thing, what's the amplitude of this? Okay, the amplitude's 4. I'm just going to note that, okay? Second thing, what's the period? It is 2 pi divided by the 2 right here, right? That's b. So 2 pi over 2 is pi, right? 2 pi over 2 is pi. Now, I'm going to go to a graph right away. And because I'm going to go in both directions, I'm going to include quite a bit of graph here. What I know is that I should have an entire sine curve between 0 and pi. Between 0 and pi. So I want to mark those points on my x-axis. Here's 0. Here's pi. Now, there were 5 important points for every sine curve, weren't there? 5 important points. There were 3 x-intercepts, a max, and a min. Yes? But if you look back at all the things we've done, that middle point, both on sine and cosine, right? This middle point was always halfway between these two, right? So what is the point halfway between these two? Pi over 2. And then there was another important point that was halfway between those two. What I mean is the point between here and here, which was pi over 4. And then there was also this point right here, which was halfway between these two. What's that? 3 pi over 2? 3 pi over 4? What is it? 3 pi over 4. So how am I doing that? I want to make sure you're good with this. Are you going off the circle or just like what you know about angles? You're just adding pi over 4 each time? You could say, okay, here's 0, here's pi over 4, here's 2 pi over 4, here's 3 pi over 4, here's 4 pi over 4. You could do it that way. But I do want to point out a way that's a little more powerful because next time, later on, we may not be able to count. So my question to you is, If I have pi over 2, and I have pi, and I'm trying to find the value right between them, how can I do it? Well, what you can do is take their average. Take the average of the two numbers. How do you find the average of two numbers? You add them together and divide by however many there are. Right? If I tell you, hey, you have 2 test grades, find the average. You add them together, you divide by 2. So if you're trying to find any two numbers on the number line, if you're trying to find the number right in the middle, you add the two numbers together and you divide by 2. That gives you the number right in the middle. So you would have to get a common denominator here, so I could convert that pi into 2 pi over 2. What's pi over 2 plus 2 pi over 2? 3 pi over 2. What's 3 pi over 2 divided by 2? 3 pi over 4, which is that value there. So I think this is more powerful to know. I mean, you don't need to use this if it's that obvious, but this is good to know for later. Okay, once I have those points, I know that the sine has 3 x-intercepts, don't I? They should be here, halfway, and at the end. Now, sine does that, right? Cosine doesn't? So I'm going to start by plotting my x-intercepts. And then I'm going to actually put the amplitude here. I know my amplitude is what? 4, -4? Still good? And you may be thinking right now, don't write this down. You may be thinking it's probably going to do this. Right? Yes? That is correct, but don't put it yet. Because it is possible later on, not on this problem, but it is possible later on that our graph actually may go down and come back up. It's a sine curve that's been flipped over. That could happen. So because of that, the only way to know which one of those it is to actually test the point. And what I mean is, take your pi over 4 and plug it into the function. So I'm going to test where's my function? Right up here? I'm going to plug in pi over 4. So we get 4 sine of, what was it, 2 times x up here? So 2 times pi over 4. That's 4 sine, 2 times pi over 4 is 2 pi over 4. 4 sine of, let's see, reduce that fraction, that's pi over 2. You following what I'm doing here? What is sine of pi over 2? So you go to your unit circle, you go to pi over 2, you look at which coordinate? The y, because it's sine, it's 1, right? So this is sine of pi over 2 is 1. 4 times 1 is 4. Which means that I can say for sure that at pi over 4, I'm up here at 4. Once I know that, I know the other one at 3 pi over 4 had to be down here. So it's going to go up and it's going to come down. So I can connect those together. Oh man, I just told you not to draw a line. I basically drew a line. It's going to go up, come down, like that. Now I've drawn one period, right? One period. For your take-home quiz to be turned in next class, I would like for you to just draw one period in each direction. All right? On this, one more period to the right, one more period to the left. But you need to mark out every single point on the x-axis where you have x-intercepts and where you have maxes and mins. Do you understand what I'm asking for? And then come back this way and do the same thing. So you should have another one over here, right? And then mark off all the points accurately. Have that all on a piece of paper by itself, not like, hey, it's in my notes. Like its own sheet of paper with your name on it. Turn it in for a quiz grade next time. All right? Sound fair? Same exact problem. I just want you to finish it off. And then your homework for this, man, a lot of what we did today was just setting things up. I'm not quite sure we're really ready to graph. Let's do this. I'm not going to give you homework. Let's let that one be the first problem for your quiz to turn in. Here's your second one. I want you to graph 3 cosine of 4x. Y equals. What I really spent a lot of time with today, that's it. So that's number 2. The first one will be the one before this. I spent a lot of time today. You might feel like we didn't get very far because we really did not get very far in 7.6. But what I did as far as setting up how to get those general solutions, x equals pi over 2 plus pi k is going to serve you very well later. All right, so we did cover good ground. I'm happy about that part. We good? All right, I'm supposed to take attendance. I could go off the quizzes, I guess. Anybody not do a quiz? Everyone? You weren't the only one? Okay, what's your last name, sir? Anna? Joel? Okay, I've got you here as being present. Okay, everybody else can go as long as you turn in a quiz with your name on it. Yes.